Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 11, Lesson number 5, working with sine and cosine using radians. Now we saw radians a few lessons ago and we talked about how to think about radians compared to degrees. We worked with radians quite a bit when we looked at the unit circle, which we're going to look at again today. And then in our last lesson, we defined the sine and cosine as being the y-coordinate and the x-coordinate where the terminal ray of an angle passes through the unit circle. The expectation is, in Common Core Algebra 2, that you're going to be working with radians on the unit circle, specifically between 0 and 2 pi. So we want to get a little bit more work with the sine and the cosine function today using radian angle measure. So let's jump right into it. All right, here we go. Radians in the unit circle. Radians are the angle measurement of choice when modeling with trigonometric functions, and we're going to see that in the coming lessons. This has to do with the fact that radians have a very physical meaning when looking at the unit circle. So let's talk about that a bit. All right, exercise number 1. The definition of radian measure is theta equals s divided by r, where s is the length of the arc intercepted by the angle, and r is the radius of the circle. If the angle is located, though, on the unit circle, how does this definition simplify? So again, let me just remind you, right? The idea of a radian is that if you have some kind of circle, ooh, that's awfully large. Let me just get out of this for a second and get this to be a little bit smaller so I've got more room. All right. So if we've got a circle and we've got an angle that's sort of located in the circle, whether it's the unit circle or not doesn't matter, right? And we've got theta and we've got an arc length s and a radius r, right, then we define the radian angle as being the arc length divided by the radius of the circle. Okay, and from that, right, we got the fact that when we do a full rotation around any circle, there are 2 pi radians, because that is simply the ratio of the circumference to the radius. But in the unit circle, right, the whole point of the unit circle is that r, the radius, is equal to 1. So that means that on the unit circle, theta equals s divided by 1, which means the angle is simply equal to the arc length. In other words, as you travel around the unit circle, you can think about the distance that you've traveled around the unit circle, literally the distance, the length, as being equal to the radian measure that you go through as an angle. And that's a real kind of physical meaning as opposed to this like arbitrary 360 degrees that we have with angles measured in degrees. So let's just kind of like formally have that right here. Radians in the unit circle. For angles on the interval 0 to 2 pi, the radian angle measurement can be thought of as the arc length intercepted by the angle on the unit circle. So in other words, right, if we've got our unit circle, a circle centered at the origin with a radius of 1, if I think about this central angle theta in terms of radians, that is exactly equal to the length of the arc along the circle that is intercepted by the angle. All right. That being said now, let's jump in and look at that unit circle a little bit more in terms of radians. And we begin by discussing the special angles on the unit circle. It's important to become fluent with the special angles on the unit circle in units of radians. That's an expectation at the Algebra 2 level, at the pre-calculus level, and certainly at the calculus level. So let's start to think about how we can consider this. Exercise number 2. Each special angle on the unit circle is an integer multiple of pi over 6, which recall is 30 degrees, or pi over 4, which is 45 degrees. And maybe I should have even put in, or both of them, all right? Now, I want you to think about something for a second, right? If I took 360 degrees and I divided it up into 30-degree intervals, right, that would be 12 intervals. In other words, if I took this unit circle and I divided it up into 30-degree central angles, I would have sort of, if you will, 12 slices of pizza, okay? And that's what we're going to begin by doing. What we're going to begin doing is we're going to start to divide up our circle in those intervals of 30 degrees, or better yet, in terms of pi over 6 intervals for radians. Let's take a look at letter A. List all integer multiples of pi over 6 on the interval 0 less than or equal to theta less than or equal to 2 pi. Simplify any fractions that can be. Label each of these angles on the diagram. All right, now again, I want you to really appreciate this. Pi over 6 and 30 degrees, right? Pi over 6 radians is the same as 30 degrees. So that means that if I sort of let's draw in this terminal ray, that is an angle of pi over 6, and I've got my first, if you will, slice of pizza. So I'm just going to kind of write that down right here, and this is going to get kind of tight on our sheet, so just write small, if you will. All right, now, I want all integer multiples of pi over 6. Well, pi over 6 times 2 would be 2 pi over 6, but 2 pi over 6 can be reduced just as 2/6 can to pi over 3. Now notice we've got a pi over 4 sitting right there, and that's 15 degrees away from 30 degrees. I'm talking about up here. All right, so this now is pi over 3. I could write down equals 60 degrees, but I really only want to be thinking about radians right now. So I've got my pi over 6, twice that is pi over 3. All right. Now, if I go one more multiple up, I will be 3 pi over 6. That is my third slice of pi. And 3 pi over 6 reduces just as 3/6 does to pi over 2. And that then is at the top of my circle, right? That is my angle that's just going up like this, and that's pi over 2. Probably one of the most important angles on the unit circle. It corresponds to 90 degrees. And that makes sense, right? I've got 30 degrees, 60 degrees, 90 degrees. Okay, now let's go another pi over 6. That would be 4 pi over 6. 4/6 reduces just as, well, yeah, 4 pi over 6 reduces just as 4/6 does to 2 pi over 3. And that's going to be this angle. Actually, let me put that, whoops, of course. It has to grab onto both of them. There we go. Thank you. Better. Okay. And again, if you want to think about it in terms of degrees, right, I've got 90 degrees here plus another 30 degrees is 120 degrees. Let's keep going. So I get another pi over 6, and that's 5 pi over 6, and I finally have one that doesn't reduce, and that's right here. 5 pi over 6. Gotta stop doing that. Okay, so finally, we have 6 pi over 6, and that reduces down to pi, and that's right over here, right? 180 degrees, half of a full rotation gets us to a radian angle of pi. Very important. It would be great if the full rotation was pi, then I could really pretend that this was a pi. But unfortunately, the full rotation is 2 pi. So I've got pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and pi, right? And those are all, right, just taking that 360 degrees and cutting it up into 12 equal slices. Now let's move into the third and fourth quadrants, right? I can then add another pi over 6 on, and I'm at 7 pi over 6, and that's going to be right down here. Then I'll add another one on, 8 pi over 6, but that reduces down to 4 pi over 3. That one's going to be down here. Then I'm going to add another one on, 9 pi over 6, and that's reduces down to 3 pi over 2. Very important. That one's down at the bottom of the circle. 3 pi over 2. Then I'll add another one on, 10 pi over 6. Again, it reduces to 5 pi over 3. That's right here. And I've got really one more, 11 pi over 6. That's over here. 11 pi over 6. Actually, let me write it in here to be consistent. 11 pi over 6. And right, our final one really would be 12 pi over 6, which would then become 2 pi, and that would come all the way, literally full circle, back to where we began, right? Look at that beautiful division of the unit circle into these intervals of 30 degrees or pi over 6 radians. All right? Now, let's talk about letter B. Write down all the coordinate pairs for these angles on the diagram if they are already not noted. Now, when I say if they're already not noted, because I did note the coordinate pairs already at 0, pi over 2, pi, 3 pi over 2, and then back to 2 pi. These are where we get to those ugly coordinate pairs, right? So let's start to write those down. Now recall, right, the coordinate pair at pi over 6 / 30 degrees comes from that 30, 60 right triangles, and specifically it's the coordinate pair root 3 over 2, comma 1/2. Okay, the one though for pi over 3 is exactly the same coordinate pair, but reflected over the line y equals x. Literally, if I took this ray and reflected it over y equals x, I would now have the coordinate pair 1/2, comma root 3 over 2. Those are the two pairs that are most commonly confused. Never forget though, square root of 3 is larger than the number 1, right? And the x coordinate at pi over 6 is clearly larger than the y coordinate. And likewise, the x coordinate for pi over 3 is clearly smaller than the y coordinate. If that helps you kind of keep those straight in your head. Now, we will eventually get to pi over 4 and then whatever this is and this is and this is, okay? But that's going to come a little bit later in the problem. Now, as we fill out all the rest of the coordinate pairs, we do it by symmetry. And I'd like you to pause the video right now, and without looking back at the unit circle diagram from a few lessons ago, see if you can now fill in the coordinate pairs at 2 pi over 3, 5 pi over 6, 7 pi over 6, 4 pi over 3, 5 pi over 3, and 11 pi over 6. Go ahead and do that. All right, well, 2 pi over 3, all I have to do is take the point at pi over 3 and reflect it across the y-axis, and we'll have the coordinate pair, let me just erase this so that we have some room, negative 1/2, comma root 3 over 2. Likewise, pi over 6 reflected across the x-axis is going to then give us the coordinate pair negative root 3 over 2, comma positive 1/2. When I go down to 7 pi over 6, I can reflect the coordinate pair at 5 pi over 6 across the x-axis, giving me negative root 3 over 2, comma negative 1/2. At 4 pi over 3, I can reflect the coordinate pair at 2 pi over 3, giving me negative 1/2, comma negative root 3 over 2. At 5 pi over 3, I'll reflect the point at pi over 3 across the x-axis. That'll give me 1/2, comma negative root 3 over 2. And at 11 pi over 6, let me make that a little bit more clear so that we can see it better. 11 pi divided by 6, reflect the coordinate pair at pi over 6 across the x-axis, and we'll have root 3 over 2, comma negative 1/2. That little hand icon just won't get out of my way. There it is. All right. Kind of great, right? Now, we've got these. Let's talk a little bit about letter C. What do you notice about the coordinate pairs for all angles that when reduced have the same denominator? All right, and here's what I mean by that, right? I've got pi over 3, 2 pi over 3. Now 3 pi over 3 reduces, so pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Let's just kind of circle those really quickly or underline them or something in red. Pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. Let me underline their coordinate pairs really quickly. We could do exactly the same for the pi over 6's, but let's just look at the pi over 3's. When you look at those four coordinate pairs, what do you notice about them? Pause the video now and see if you can write something down that makes sense to you. Well, all the coordinates have the same absolute values, right? So 1/2 root 3 over 2, negative 1/2 root 3 over 2, negative 1/2 negative root 3 over 2, positive 1/2 negative root 3 over 2, right? All the coordinates have the same absolute values. They just differ in sign. And that's true also of the pi over 6's. Right? Now, that's due to the symmetry of the unit circle. And what's really kind of cool about it is that you can really look at this and say, well, pi over 3, we're going to bring back a term we haven't seen since the first lesson of this unit. Pi over 3 is the reference angle for 2 pi over 3, 4 pi over 3, and 5 pi over 3, right? This angle here is the same as this angle here, and is the same as this angle here, and is the same as this angle here, right? The same thing is true of pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6, right? And that's why you kind of get these same coordinates. Now, the one thing that we haven't done yet is dealt with the pi over 4's, all right? So let's get back and take a look at the pi over 4's really quick. There'll be less of those, thankfully. Letter D. Now do the same for all integer multiples of pi over 4. Now, pi over 4 is a very, very important angle. I mean, exceptionally important, because it's half of pi over 2. Specifically, right, pi over 4 is 45 degrees. It's half of 90. Okay, so our integral multiples, right, are pi over 4, comma 2 pi over 4, but that's pi over 2 and we've already labeled it, 3 pi over 4, which is right here, and I'm going to just have to sneak that in, 3 pi over 4. Okay, and that would be 90 degrees plus 45 degrees. So if you want to think about it in degrees, that would be 135 degrees. Then we've got 4 pi over 4, which is pi, and we've already got that labeled. Then we have 5 pi over 4, which is this guy right here. And I have to just sneak it in. Okay, back down. Then we have 6 pi over 4, and that's 3 pi over 2, and that's at the bottom of the circle again, 270 degrees. Then we have 7 pi over 4, and that's our 45 degrees sort of version in here. And then we've got our 8 pi over 4, which is 2 pi. So one way to divide up the circle, right, with special angles is by thinking about these 30-degree intervals. Another way of thinking about it is with 45-degree intervals. And there, we're really slicing the circle up into 8 equal-sized sections. 0, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi over 4, right? We're slicing them up into these, eighths, if you will, which is kind of the way a pizza gets sliced up. Now, what we also want to do is put our coordinate pairs down. Now, that 45-degree angle, that pi over 4 radian angle, has that dual coordinate pair that's a little bit obnoxious, root 2 over 2, comma, root 2 over 2. Square root of 2 over 2, comma, square root of 2 over 2. Now, just like with the angles that were at the pi over 6 and pi over 3, we can fill in the rest via symmetry. Pause the video now and go ahead and fill in the coordinate pairs at 3 pi over 4, 5 pi over 4, and 7 pi over 4. Pause the video now and go ahead and do that. All right, so up here, just kind of squeezing it in, we'll have negative square root of 2 over 2, comma, positive square root of 2 over 2. Down here, we will have negative square root of 2 over 2, comma, negative square root of 2 over 2. And over here, we will have square root of 2 over 2 and negative square root of 2 over 2. Okay, there we go. And again, just like we pointed out in letter C, right, for any of these angles that are irreducible with denominators equal to 4, they all basically have the same coordinate pair, root 2 over 2 comma root 2 over 2. The only question is x positive or negative? Is y positive or negative? And that is all determined by what quadrant you're in. Okay, so where do we go from here? An angle and its reference angle. Let's talk about that. Sine and cosine of angles and reference angles. The sine and cosine of any angle, not just the special angles, but any angle will have the same absolute value as the sine and cosine of its reference angle. This is due to the symmetry of the unit circle, or of any circle. Now again, we're just working today with the special angles in terms of radians, but this actually works whether you're talking about degrees, radians, whether they're special angles or not special angles. And keep in mind, the reference angle, right, is an angle between 0 and 90 in terms of degrees, or between 0 and pi over 2 in terms of radians, all right, that the terminal ray makes with the x-axis. So how do we use this? Well, let's take a look at exercise number 3. Given two angles, pi over 6 and 5 pi over 6, do the following. Letter A. State the sine and cosine of pi over 6. Well, keep in mind, right, the angle or the coordinate pair at pi over 6 was root 3 over 2 comma 1/2, right? That was our coordinate pair at pi over 6. And remember, when we defined sine and cosine in our last lesson, we defined the cosine as being the x-coordinate of the coordinate pair, and the sine as being the y-coordinate of the coordinate pair. So we can now say that the cosine of pi over 6 is equal to root 3 over 2, and the sine of pi over 6 is equal to 1/2. Okay, great. Now, letter B. What quadrant does the terminal ray of 5 pi over 6 lie in? Okay, now we just went through this, so you could look at the diagram on the front side of the sheet. That would be fine, all right? But I also want you to just be able to think about this number, 5/6. Why do I want you to be able to think about this number? Right? Well, 5/6 is obviously less than 1, and it's greater than 1/2. Okay? And the reason that I want you to think about 1/2 and 1 is that on the unit circle, remember, right, 0, 1/2 pi, 1 pi, right? So 0 degrees corresponds to 0 radians, 90 degrees corresponds to pi over 2 radians, and 180 degrees corresponds to pi radians. So because 5/6 falls between 1/2 and 1, it must fall in quadrant 2, right? We've got this quadrant, right? 0, pi over 2, pi, 3 pi over 2. 5/6 has to fall between 1/2 and 1. All right, now letter C. Based on B, what must be the signs of sine 5 pi over 6 and cosine 5 pi over 6? Well, sine of 5 pi over 6 must be positive. Well, I'll just say positive because it's equal to the y-coordinate, right? And in the second quadrant, the y-coordinate is positive. And cosine of 5 pi over 6 must be negative because it's the x-coordinate, right? So in the second quadrant, the x-coordinate is clearly negative, the y-coordinate is clearly positive, so the sine must be a positive number and the cosine must be a negative number. So now letter D, state the values of sine 5 pi over 6 and cosine 5 pi over 6. Well, the reference angle for 5 pi over 6 and for 5 pi over 6 is pi over 6. So the cosine of 5 pi over 6 must be equal to negative root 3 over 2, and the sine of 5 pi over 6, by the way, the parentheses aren't necessary around the angle there, but you can have them, is equal to positive 1/2. So here's the beauty of the reference angles, especially when it comes to dealing with the special radian angles. You just need to know the values in the first quadrant. Because if you know the values in the first quadrant and you can locate where the terminal ray lies, then you simply take these and say, well, I know in the second quadrant sine is positive, so sine of 5 pi over 6 must be the sine of pi over 6, and they're both 1/2. And cosine of 5 pi over 6 must be negative. Well, I know cosine of pi over 6 is positive root 3 over 2, so cosine of 5 pi over 6 must be negative root 3 over 2. And that's in fact exactly what we see in this horribly, terribly complicated diagram. Here at 5 pi over 6, the x-coordinate is negative root 3 over 2, and the y-coordinate is 1/2. All right? So the key is, if the angle is reduced, right, the radian angle is reduced, then its reference angle is simply going to be that particular angle. And if you know the sine and cosine of whatever that angle is, then you can figure out the sine and the cosine of the overall angle if you just know what quadrant its terminal ray lies in. Okay, so let's get some practice on that. Let's talk about it. Exercise number 4. For each angle below, state both its sine and cosine values. So notice I've got all the other first quadrant angles, pi over 4, pi over 3, and pi over 2. Pi over 2 isn't really a first quadrant angle because it lies literally on the y-axis. But what I'd like you to do, actually, let's first write down the coordinate pairs, right? For pi over 4, the coordinate pair is root 2 over 2, comma root 2 over 2. For pi over 3, the coordinate pair is 1/2, comma root 3 over 2. And for pi over 2, the coordinate pair is 0, comma 1. That one's easy. That's the one that just stands straight up, right? Due north, so to speak. So given these coordinate pairs, what I'd like you to do is now state both the sine and the cosine values of each one of these angles. Pause the video now and go ahead and do that. All right, well, the first one's not very interesting because they're both the same coordinate, or they're both the same number. Cosine of pi over 4 is the x-coordinate, so it's root 2 over 2. Sine of pi over 4 is root 2 over 2. All right, on the other hand, for pi over 3, the cosine of pi over 3 is going to be 1/2, and the sine of pi over 3 is going to be root 3 over 2. And for pi over 2, the cosine of pi over 2, or 90 degrees, is 0, and the sine of pi over 2 is equal to 1. And there we have it, right? Now, those are just sort of those first quadrant angles along with that 90-degree angle there at pi over 2 radians. But now let's use those to think about exercise number 5. For each of the following angles below, do the following. 1, state its reference angle. 2, state the quadrant its terminal ray lies in. And 3, state its sine and cosine values. Draw a rotation diagram if it helps. All right, great. So the reference angle is going to be the easy part, because when I look at 4 pi over 3, its reference angle is equal to pi over 3. Okay? So awesome, because that means everything I really sort of need to know is sitting right up here. All right? That's going to be the coordinate pair that's key when I deal with 4 pi over 3. Now I have to think about what quadrant it lies in. And again, what I really want to be thinking about is 4/3. Now, if you absolutely, positively had to, and feel free to do this, you could convert 4 pi over 3 to degrees. You could do that, all right? But I also want you to, again, think about it this way. I've got this circle. I've got 0, 1/2, 1, and 3/2. Now, there's a pi attached to them all. Okay? Right? 1/2 pi, 1 pi, 3/2 pi, and 2 pi. Where does 4/3 lie? Well, 4/3, right? 4/3 is equal to 1 and 1/3. 1 and 1/3 is bigger than 1, but it's less than 1 1/2, right? So 4/3 lies in the third quadrant, right? We're in the third quadrant. Now, how does that now help us? Well, number 3, state its sine and cosine values. Again, for pi over 3, I know that that's 1/2 comma root 3 over 2. In the third quadrant, both the x and the y coordinates are negative. So let's start with cosine. So the cosine of 4 pi over 3 is going to be negative 1/2. And the sine of 4 pi over 3 is going to be negative root 3 over 2. So when I'm looking for the sine or the cosine of any of the special values, the first thing I do is identify the reference angle. The second thing I do is think about what quadrant the terminal ray lies in. That helps me determine whether sine and cosine are positive or negative. And then I just need to know the coordinate pair for my reference angle, and that will help me figure out what the sine and cosine are of the actual angle I'm dealing with. Why don't you go ahead and try to do this in letter B? Okay, well, again, the reference angle is the easiest part, right? The reference angle in this case is pi over 4. The reference angle will always be that for these radian measures, which is a reason to kind of like radians, right? Now, when I think about pi over 4, its coordinate pair is root 2 over 2, root 2 over 2. It's that nice 45-45 right angle. So now I'm thinking about the angle 3 pi over 4. Well, again, if I think about this, I'm thinking about the number 3/4, and 3/4 is between 1/2 and 1, and therefore 3 pi over 4 has a rotation diagram that kind of looks like this, right? So we are in the second quadrant. In the second quadrant, the x-coordinate is negative, the y-coordinate is positive, so I can now say that the cosine of 3 pi over 4, which is the x-coordinate, will be negative root 2 over 2, and the sine of 3 pi over 4 will be positive root 2 over 2. And there we have it. Now, you won't need to deal with negative angles nearly as much, but we should still be able to deal with any negative angle that falls between 0 and negative 2 pi. All right, so let's take a look at letter C. Here we have an angle of negative 5 pi over 6. So what I'd like you to do is, again, take your best shot at this. Reference angle should be easy. Same thing, right? The toughest part then is your quadrant, okay, but I'm hoping you can figure that one out as well. Pause the video now and see what you can do. Okay, well again, reference angle, piece of cake. Reference angle is pi over 6. Excellent. Now remember, its coordinate pair is root 3 over 2, comma 1/2. There we go. Now, negative 5 pi over 6. Well, the key here, right, we've got to go clockwise. This is going to be 0. This is going to be negative 1/2 pi. And this is going to be negative pi, right? And then it's going to be negative 1.5 pi and negative 2 pi. Well, negative 5/6, right, this number, negative 5/6, is going to be into the third quadrant, right? Because 5/6 is between 1/2 and 1. Negative 5/6 will be between negative 1/2 and negative 1. So we're talking about the third quadrant, which means both of these quantities are negative, and that means that the cosine of negative 5 pi over 6 is going to be negative root 3 over 2, and the sine of negative 5 pi over 6, maybe I'll put parentheses around here so it doesn't look like subtraction, is going to be negative 1/2. All right, and that's it. Let's keep working. Let's take a look at one last issue. The sine and the cosine function are often parts of more complex functions, and we're going to start really digging into those in the next few lessons. But let's take a look at a fairly easy problem right now. Exercise number 6. If f of x equals 5 times the sine of twice x plus 8, then determine the value of f of 3 pi over 4. All right, I'd like you to pause the video right now and see if you can do this without using your calculator at all. See what you can do. Now I say try to do it without your calculator because you could plug this into your calculator. Let's be very honest. The problem though with that is that you might end up with kind of a scary looking answer that has radicals and things like that in it, in which case you're going to get a decimal version on your calculator in all likelihood. But let's take a look at this. So we've got f of 3 pi over 4. All right, let's just be kind of true to what we're doing here. We've got the sine of 2 times 3 pi over 4 plus 8. Okay, now I might as well simplify what's inside here first. The 2 and the 4 will cancel, and that will leave me with the sine of 3 pi over 2 plus 8. Now I have to think about what the sine of 3 pi over 2 is. Well, where is that on my unit circle? On my unit circle, 3 pi over 2 is one of my what are called quadrantal angles. All right, it's one of the angles that's either at the top, the bottom, the left, or the right of the circle. It's specifically down here where we have a coordinate of 0, -1. Okay, the sine is the y value. So the sine of 3 pi over 2 is equal to -1 because it's the y coordinate. So this is all 5 times -1 plus 8, which is -5 plus 8, which is equal to 3. And there we have it. All right, let's wrap this up. So one of the expectations that you have coming out of this particular course is that you can deal with the sine and the cosine and other trig functions that are yet to be named. You can deal with the sine and the cosine of all these special angles and their multiples between 0 and 2 pi and 0 and -2 pi. All right. The key though is really just knowing those coordinate pairs in the first quadrant, specifically pi over 6, pi over 4, pi over 3, and then the quadrantal angles at 0, pi over 2 pi, and 3 pi over 2. The reason why those first quadrant angles are so very important is when you then look at an angle like, let's say, 5 pi over 3, you can say, well, 5 pi over 3 can't be reduced, and therefore its reference angle is pi over 3, so it will have a sine and a cosine that have the same absolute values as the sine and the cosine of pi over 3. You then just have to determine what quadrant the terminal ray of 5 pi over 3 lies in, and I encourage you to do that by thinking about fractions and comparing it to where the quadrantal angles are on the circle. But if you need to, you can also take 5 pi over 3 and convert it into degrees. By the way, 5 pi over 3 is 300 degrees, and that would clearly put you into the fourth quadrant, where you could then say that the cosine is positive and the sine is negative, and then based on pi over 3, you could come up with the values for sine and cosine of 5 pi over 3. All right, I want you to get a lot of work with this on the homework. You want to come out of Algebra 2 really having a good fluency with these special angles in terms of radians. And that's tricky given that this is the first time you've dealt with the radian measure of angles, and boy, that unit circle's pretty ugly as well. But you will get better at them, and it will pay dividends throughout the rest of this unit and when you take both pre-calculus and calculus, which I do hope you take. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.